So this is momentum, is the next part of our energy conversation. Momentum really all has to do with collisions. So when you have anything hit something else, you're going to cause a momentum shift. We have a couple different types of collisions. We have elastic and inelastic. Elastic is when something bounces off of itself. You have, a ball hitting a wall, it's going to bounce off. Inelastic is when they stick together. So if you get like a car wreck and you get linked on the car in front of you. Mathematically, it's pretty straightforward. We use the Greek letter rho, P, as usual, you right there for momentum. It is just mass times velocity. So two things we've already measured a lot of, mass and velocity. We've seen a lot of that in the energy unit. But finding the momentum of one object by itself, this car is moving at 10 meters per second. We could find the momentum of just him in kind of a boring situation. So until the collision happens that it gets a little more interesting, and we have the conservation of momentum. We talked about conservation this week with energy. Momentum is the next piece. So we say the momentum before the collision is equal to the momentum after, right? So what this really fans out to is you find the momentum, it's a summation. It's the momentum of all the particles or all the objects in the system before and after, B and A. So this fans out, you see it on your formula sheet, as mv plus mv equals mv plus mv. And this could be 3 objects, 4 objects. We're going to start with 2 just to learn how to do the math, right? So the questions are always about, during a collision, there's going to be a transfer of energy, the momentum is going to shift. What happens after the collision? So we have this car here parked. This is a story of when I was 16, I rolled up on a guy at a stoplight and I slammed into him. We slid into the intersection. The question always kind of comes, well, after the collision, how fast are they moving? What is their velocity after the collision? So we're going to run through that. We're going to find the momentum of each object before they crashed and each object after they crashed. That's going to be an inelastic collision. They're going to stick together. So we have the first car is moving at 200 times his velocity is 10. The other guy is also a 200 kilogram car, but he is not moving at all. So all we have is this momentum, that 200 times 10. So we get 2,000 kg ns. Ns is the unit for momentum. There is no special joules or newtons, it's just kilogram meters per second. So the amount of momentum in the system is 2,000. This one's 0, right? 200 times 0. So we added to that 2,000. We're just left with the 2,000. So what we're looking for is after they collide, how fast are they moving? What is the velocity? Well, I told you they stuck together. If they stick together, their velocities are the same. So when you're stuck with something, you're moving as fast as the object in front of you. So we're going to figure that out by factoring that velocity out. What that usually looks like is you have the masses added together times the velocity of both of them. So you can FOIL that back in, right? Or distribute, I think that's the math word. We know their masses, right? They're both 200. That doesn't change in this collision. And we're looking for V. So I got 2,000 equals 400 V. We just divided by that 400. And I believe you're left with 5 meters per second. Now conceptually that should make a little intuitive sense, right? We're going 10 meters per second. We hit a car at the same mass. We're doubling our mass, which means our speed drops by half. Mass went up by 2, the velocity had to go down by 2, a factor of 2. So momentum after was 5. They're both sliding into the intersection at 5 meters per second. Now we do this a lot in like forensics, right? They'll say they hit and they leave some brake marks out to the intersection. We did that problem with Back to the Future, right? We could work it backwards and figure out was someone speeding, who's at fault. You can look at whether they're drunk driving, where the tracks are. There's all kinds of interesting forensics you can do with that. So, your goal today is to prove, is that true? All right, this is the conservation of momentum. We're going to set up a collision and figure out, is that true? So basically what you're going to do, and you'll have the handouts already on your table, is you're gonna have a ramp, some marbles. You're gonna set up a little track and a little path for them to go down. You got a ramp up here and then your straightaway. Usually we get on the ground for this. One marble here, one marble here. You're gonna let the white marble go, or whatever, the top marble. It's gonna go down the ramp. You need to know the velocity right here. Hopefully at this point in physics, you know how to do that. You've done that in a lot of labs, final velocity, final ramp. Cool. They're then going to collide. You want this to be in a straight line. You don't want them bouncing or going sideways, so maybe you lay down some track or meter sticks or whatever to keep them going in a straight line. After they collide, you need to measure, the white ball is gonna go somewhere, the black ball is gonna go somewhere. You need to measure both of those distances. It's pretty easy. They're gonna stop moving. How far away did they roll? But the hard part about it is you need to measure how long it takes them to get there. So you are timing both balls independently of each other. So divide up the work, right? One person's watching the front ball, one person's watching the back ball. You need the time for both. They're gonna be different. Unless they're stuck together, they might be moving together. Depends on how you set up your ramp, right? The velocity coming in. So once you know both of these X and T values, we've done that lab too, you should be able to work out how fast are they going after they got hit. They're gonna come to rest, so the final velocity is gonna be 0. But what I'm looking for is the initial velocity of both marbles after the collision. So that you'll have all 4 velocities to plug into this equation. Now the black one was not moving to start with, so this V is 0. So we're really looking for 3 velocities. Down the ramp, and both of them while they are in motion. So that we can prove, we're gonna solve both sides of the equation. So this 2,000 should come out to be on both sides in the example. So you're gonna measure each piece independently. I should be back before class is over, so I can answer any follow-up questions that you get set up. Good luck.